Welcome. Today we will see design of spur gear. Now these images are there. This image shows spur gear. Spur gear is used to connect two parallel shafts. Spur gear is having teeth parallel to the axis of the shaft. Also spur gear is used to transmit motion or power at a speed ratio of up to 6:1. This is the image of spur gear terminology. Now first point in design of spur gear is gear tooth failures. The two basic modes for gear tooth failures are: first, breakage of the tooth due to static and dynamic loads, and second, surface destruction. Now we will see first breakage of tooth. The complete breakage of the tooth can be avoided by adjusting module and face width so that the beam strength of the gear tooth is more than the sum of static and dynamic loads. The static beam strength of a gear tooth was suggested by Wilfred Lewis. The dynamic load is caused due to small machining errors resulting into inertia and impact loads on the gear tooth. Now surface destruction. The wear of gear tooth takes place due to the combined action of rolling and sliding. Rolling causes contact stresses and sliding causes rubbing action. Pinion is subjected to more rubbing action as it rotates faster than the gear. The principal type of gear tooth wear are abrasive wear, corrosive wear, pitting and scoring. Now we will see one by one. First is abrasive wear. Now this diagram shows the severe abrasive wear of the gear teeth. See that. The tooth surface is scratched by foreign particles in the lubricant such as dirt, rust and weld spatter of metallic debris. This can be reduced by oil filter using high viscosity lubricants and surface hardness. Next is corrosive wear. See, these figures are there. Corrosion of gear tooth takes place. The corrosion of the tooth surface is caused by corrosive elements such as extreme pressure additives present in the lubricating oils and foreign materials due to external contamination. These elements attack the tooth surface, resulting in the fine wear uniformly distributed over the entire surface. The corrosive wear can be controlled by complete enclosure of the gears, selecting proper additives and replacing the lubricant at regular intervals of use. Pitting. It is a type of fatigue failure caused by repeated applications of stress cycles. Pitting phenomenon is of two types: initial pitting and destructive pitting. Now we will see first of all initial or corrective pitting. It is a localized phenomenon characterized by small pits at high spots. Now you just see this figure. Some of the gears on some of the gear teeth, they are having these small pits are there on the gear teeth. Such high spots are progressively worn out and the load is redistributed. Initial pitting is caused by the error in tooth profile, surface irregularities and misalignment. These controlled by precise machining of gears and their correct alignment so that the load is uniformly distributed across the full face width and the dynamic load is reduced. Now destructive pitting. See that destructive pitting. On every teeth, these more number of pits are there. Large pits are there. It is a surface fatigue failure which occurs when the load on the gear tooth exceeds the surface endurance strength of the gear material. This type of failure is characterized by pits which continue to grow, resulting in complete destruction of the tooth surface. In some cases, this may even break the tooth permanently. This type of failure can be avoided by ensuring that the wear strength of an entire gear tooth is more than the sum of static and dynamic loads. The surface entrance strength is a function of the hardness and can be increased by improving the surface hardness of the gear tooth surface by using an appropriate heat treatment process. Now last, that is scoring. The oil film between the gear teeth may break down under excessive surface pressure, high sliding velocity and inadequate supply of lubricant. This results in generation of excessive frictional heat and overheating of the contact surfaces of gear teeth. This may lead to metal contact. Scoring is a stick-slip phenomenon in which alternate welding and shearing takes place rapidly at the high spots. This increases the wear rate faster. Scoring can be controlled by selecting proper surface speed, surface pressure and flow rate of lubricant to keep the temperature of contacting surfaces within permissible limits. The bulk temperature of lubricant can be reduced by providing fins on the gearbox, air cooling by a fan or circulating cold water. This is the figure of scoring. You just see how the scoring takes place. After the initial scoring, if the load, speed or oil temperature increases appreciably, then severe scoring sets in with heavy metal to metal contact. Scoring is normally predominant over the pitch line. This is the pitch line, see that. This is the pitch line where actual contact takes place, line contact. Pitch line region, since elasto-hardening of lubrication is the least at the region, in dry running surfaces may cease. Now we will see force analysis. Now the diagram shows pinion with center O1 and gear with center O2. Pinion is the driver, gear is the driven. This is the pressure line along which this normal force Pn acts. This alpha is the pressure angle. This P is nothing but pitch point. Pinion rotates in anti-clockwise direction, therefore gear rotates in clockwise direction. In gears, power is transmitted by means of a force exerted by the tooth of the driving gear on the meshing tooth of the driven gear. Figure shows the tooth of the driving pinion exerting a force Pn on the tooth of the driven gear. According to the fundamental law of gearing, the resultant force Pn always acts along the pressure line. The resultant force Pn can be resolved into two components, tangential component Pt and radial component Pr at the pitch point as shown in figure. Therefore, this Pn, it is resolved into two components. This Pr is nothing but radial force or separating force. This Pt is nothing but tangential force, due to which torque is transmitted. The tangential component Pt is a useful load because it determines the magnitude of the torque and consequently the power which is transmitted. The radial load Pr is a separating force which is always directed towards the center of the gear. The torque transmitted is given by Mt is equal to 16 to 10 raised to 6 into kilowatt divided by 2 pi n, where Mt is equal to torque transmitted by gears in Newton mm. Kilowatt is equal to power transmitted by gears in kilowatt. N is equal to speed of rotation in RPM. Therefore, the tangential component Pt acts at the pitch circle radius. Therefore, by the gears is given by Pt into d dash divided by 2 is equal to Mt, where d dash is equal to pitch circle diameter of the pinion. Therefore, Pt is equal to 2Mt divided by d dash. Therefore, from this figure, Pr, that is tan alpha, is equal to Pr upon Pt. Therefore, Pr is equal to Pt tan alpha. Therefore, substituting the value, the resultant force Pn is given by Pn is equal to Pt upon cos alpha. The above analysis of the gear tooth force is based on the following assumptions. First, as the point of contact moves, the magnitude of resultant force Pn changes. This effect is neglected in the above analysis. Second, it is assumed that Only one pair of teeth takes the entire load. At times there are two pairs which are simultaneously in contact and share the load. This aspect is neglected in the analysis. Third, the analysis is valid under static conditions, that is when the gears are running at very low velocities. In practice, there is dynamic force in addition to force due to power transmission. The effect of this dynamic force is neglected in this analysis. Now we will see number of teeth. In the design of gears, it is required to decide the number of teeth on the pinion and gear. There is a limiting value of the minimum number of teeth on the pinion. As the number of teeth decreases, a point is reached when there is an interference and the standard tooth profile requires modification. The minimum number of teeth to avoid interference is given by Z minimum is equal to 2 divided by sin square alpha. In practice, giving a slight radius to the tip of tooth can further reduce the value of Z minimum. Theoretical and practical values of the minimum number of teeth on the pinion are as follows. Therefore, this is a table for different pressure angle. What are the theoretical number of teeth and what are the practical minimum number of teeth. A pressure angle for 14.5 degree, Z minimum theoretical is equal to 32, Z minimum practical is equal to 27. For 20 degree pressure angle, Z minimum theoretical is equal to 17, Z minimum practical is equal to 14. For 25 degree pressure angle, Z minimum theoretical is equal to 11, Z minimum practical is equal to 9. For the 20 degree full depth involute system, it is always safe to assume the number of teeth on the pinion as 18 or 20. This does not require any modification in the profile. Once the number of teeth on the pinion is decided, the number of teeth on the gear is calculated by using the velocity ratio, that is I is equal to ZG divided by ZP. There is a concept of hunting tooth for uniform distribution of tooth wear. Suppose ZP is equal to 20 and ZG is equal to 40. Then after every 2 revolutions of the pinion, the same pair of teeth will engage. If however we take ZP is equal to 20 and ZG is equal to 41, the pinion will rotate 41 times before the same pair of teeth will engage again. This extra tooth is called the hunting tooth. It results in more even distribution of wear. For the provision of hunting tooth, it should be permissible to alter the velocity ratio slightly. In a multi-stage gearbox consisting of 2 or 3 stages, the velocity ratio at each stage should not exceed 6:1. The intermediate speeds in this case are arranged in geometric progression. If I is the total transmission ratio, that is ratio of the angular velocity of the first driving gear to the last driving gear, then the speed reduction at each stage, that is I, is obtained in the following way. For 2 stages, I is equal to square root of I dash. For 3 stages, I is equal to cube root of I dash. As the number of teeth increases, the pitch circle diameter and the size of the gear wheel also increases, thus increasing the cost. Therefore, the number of teeth on the pinion as well as on the gear should be kept as small as possible. Now we will see face width. In the design of gears, it is required to express the face width in terms of the module. In the Lewis equation, it is assumed that the tangential force Pt is uniformly distributed over the entire face width. If the face width is too large, there is a possibility of concentration of load at one end of the gear tooth due to a number of factors like misalignment, elastic deformation of shafts, and warping of gear tooth. On the other hand, gears with a small face width have a poor capacity to resist the shock and absorb vibrations. They also wear at a faster rate. A narrow face width results in a coarse pitch. In practice, the optimum range of the face width is 8 times module less than B less than 12 times module. In the preliminary stages of gear design, the face width is assumed as 10 times module. Okay, thank you very much. In next lecture we will see beam strength, wear strength and effective force.